All right, let's take care of this last little bit of this unit 6. Okay, so this will kind of finish up our sampling distributions. So what we want to do is we want to really solidify the notation that we have for population versus sampling distribution of proportions and means. Okay, and then we're also on the next page going to take care of some problems where, in order to compute the probabilities and such, we've really got to pay attention to, is this a problem about the population, or is this about the sampling distribution? Because when we do our normal model math, that the difference between those will play into which standard deviation we use. Okay, so here we go. Let's take a look at these first. So you can see here's all of our definitions, okay? And we're just going to go along here. So here I see this one is our standard deviation, and then it's the standard deviation of what? Those p hats. What are the p hats? They are the sample proportions. So that was K. And here was the standard deviation of the X bars. So that's the standard deviation for those sample means. Okay? So those are the variability in sampling distributions. All right, but this one right here, this standard deviation, that one is for the whole population. So that's that standard deviation of the population. Okay. Now, we talked about when we did our timer activity, you had 30 different times. Each one of your times was an individual piece of data. So you had 30 X values. So that was individual pieces of data. Okay. And you then had a sample size of 30 because you had 30 pieces of data. So that C is that letter N is your sample size. All right. Then you took all those 30 times when you tried to hit the timer at exactly 5 seconds and you did X bar. That's your mean, the average of your 30. So your sample's average. So that's your sample mean, letter E. Okay. Now, P, the just plain P versus P hat. So P is going to be that population proportion versus P hat, which is that one you get when you got a sample, what you got when you got a sample. Okay. Now then, here's just plain mu. So look, here's a few mu's. This mu is that mean of the whole population. So I think that that's A, mean of the population. Okay. But then these last two are different. So here's the mean of the p hats. So that's the mean of the sample proportions. That's J. And then the last one was mean of X bars. So that was the mean of all the sample means. Okay. So, knowing those notations is going to help you when you are understanding how important it is to pay attention to the difference between population distribution or samplings distribution. So, here is a reminder of our formulas that we were dealing with for proportions versus means. So, here was our for proportion sampling distribution. Here was our mean, and here was our standard deviation. And you used this on yesterday's assignment. For means, sample means, there was our mean and standard deviation for that. Okay, so these are on your formula chart. So that's nothing new that you have to memorize. Now, let's take a look at this next page. So what I have, let's take a look at this. So we're going to take a look at these mean problems and pay close attention to if we're discussing the population or a sampling distribution. So what you need to remember is what this looked like back here when we were talking about a population versus the sampling distribution, the ones that were made from X bars as opposed to being made from all the individual X's. Okay, so, so here we go. This first problem says that the weight of potato chips in a medium-sized bag is stated to be 10 ounces. So you have a bag, it says that it's 10 ounces, okay? So the amount of that the packaging machine puts into these bags is believed to follow the normal model with a mean of 10.2 and a standard deviation of 0.12. So paying attention to the fact that they say the normal model is the population is normal model is a big deal. Okay, and let me tell you why. If you remember back here, and I think it's actually at the bottom of this page. Yep, there it is at the bottom. Okay, so let me go down to that and show you it. See, if you are told that the population is normal right here, then if the sample size is a small sample size, no biggie. It's still going to be approximately normal. Now, bigger, of course, large sample will, of course, be approximately normal. But this is the one case right here. This is the one case in which it is okay to be a small sample and you can do normal model math. It's because we were told that the population was normal. These, it's not safe. These small samples, it's not safe to do normal model math with those. Okay, so we're dealing with this. We know the population is normal, so anything that comes out of it, we can do normal model math with. So here we go. So the first question says, what fraction of all bags sold are underweight? So it's just asking the proportion of all of them. So it's referencing just the parent population because it's just referencing all the bags, not a sampling distribution. That would say what samples have a sample mean of this much or that much. So this proportion is asking about individual bags. Here comes the information that we can gather from that. The mean, the standard deviation, the X is 10, and our Z-score. So then underweight, of course, is that lower area. So 4.75% of all bags that come off that assembly line are going to be underweight. You will be getting robbed. You will not be getting your 10 ounces of chips. Now, take a look at this next one. Some of the chips sold are underweight, okay? And they're sold in bargain packs where you get 3 bags of chips. Okay, so what is the probability that none of the 3 is underweight? So this is a big deal, and this is very much like what might happen on an AP free response question, where you use an answer from a previous problem to answer a subsequent part. Well, if you can't do part A, then you could, even if you don't know the answer to part A or you get part A wrong, if you use that correctly in the subsequent parts, you get full credit. Okay, so keep that in mind. Now, I'm going to be using the fact that I just computed in part A that said the probability of underweight is 0.0475. Okay, so it says, what's the probability that none of them, so the first one's not underweight, and the second one is not underweight, and the third one is not underweight. So if you remember, this is like from the unit before Christmas, where all 3 of them are not underweight. So this one's not underweight, and this one's not underweight, and this one is not underweight. So there's an 86.42% chance that none of them will be underweight. That's good. You like that. That's a high probability that everything's going to be all good. Okay. Next question. Here we go. So now, let me move this up here. So now we're wondering, okay, so what is the probability that the average weight of 3 bags? Okay, so think about what this is saying. This is saying average together 3 bags worth of weight. That's a sample of size 3. That's an X bar. That makes a sampling distribution. So we're now talking about a sampling distribution of a small sample size of size 3. So you can see over here on the left, look at what I've got going on here. Okay, so this, again, so I wrote here, this problem is now about a sampling distribution of samples of size 3. And I know this because it asks about the average weight of 3 bags. Therefore, imagine that this is a bunch of X bars, and we're going to see what that is. Okay, so it's referencing the parent population. All right, but what did it ask? Oh, what's the probability that the average of 3 of them is below the stated amount? Okay, so here we go. Look at my facts over here on the side. There's our population mean, our standard deviation, our sample size is 3. The average of the 3 is 10. Okay, now they should all this averages should all center around 10.2, but look at this standard deviation. It for the samples. This standard deviation for the sampling distribution of samples of size 3 is smaller. It is now 0.069, not 0.12. Let me just let you visualize what's happening here. If we looked back at this page here, this is really important that you understand what's happening here. So if we visualize this picture here, here's our population, and then here is our sampling distribution of a small sample, and then our sampling distribution of a large one. Well, let me just demonstrate this with a line. If I have this line, I'm going to color in here. Let's see if that'll work. Okay, let's say that this represents where 3 bags or underweight. Okay, so there is the line. That red line is 10 ounces. And so we know the average is 10.2. Anything below this line is going to be below 10 ounces and will be underweight. So what we computed in part A was this area here. Okay, we computed this underweight area right here to be 4.75 ounces. Okay, so 4.75% of all the samples, or nope, all the bags are underweight. But now we're saying, hey, what's the probability that we find an average of 3 samples below there? Do you see how this standard deviation is smaller? It has, because it is less varied and it has sucked this in. Tell me about the comparison. How likely is it to find an individual bag that is underweight compared to how likely is it to find an average of 3 bags that are underweight? Okay, so that's what this is about. And we're in a second going to do one that says, what's the probability of finding a case of 24 bags that average and underweight? There's pretty much no way you're going to get an average of 24 bags that are underweight because, see, this standard deviation is so small and they're so closely clustered around the mean of 10.2. All right, so that's physically what's happening with this problem. So let's take a look at how the values compute out. So let's see here. All right, so we did our z-score, and look, only a 0.19% chance, so a teeny tiny bit. There was a teeny tiny bit, a 0.19% of that chance that it will be the average of 3 bags will be below 10 ounces. So now, what's the probability that the average of 24 bags is going to be there? Well, what's that do? That made this standard deviation smaller, as I showed you in the picture. Okay, and so look, that standard deviation being smaller. Now then, whoa, look at that. 8.33 standard deviations below the mean. Mind blown. That is virtually a 0% chance that the average of all 24 bags will be underweight. Okay? So that's what's happening. So it's a matter of where the smaller standard deviation makes it less likely for that larger sample to be underweight. Okay, let's see what's next. So here we go. Now, explain why you suspect that the distribution that is filled with individual times that people work at their job. So we're talking about things like how long a person, so how many years has a person stayed at a job? I've been at Alito, I think this is now my 16th year, maybe my 17th, okay? So how long have you stayed at your current job? And the one before that, I had stayed there for 7 years. So people stay at their jobs for different lengths of time. So look here. Why do you think it would be skewed to the right? The distribution? Well, look at this picture. I showed you a picture of what it might look like. These are individual, see these X's? Those are individual people. Most people are working at the same job for what they say the average is of 6.2 years, which is what I did at my first teaching job, okay? 7 years. But look, why is it skewed right? Here's my father-in-law right here. He started and he ended at the same location. He worked. Now, it wasn't the same position for all those years, but he was with the same company for his entire career. So you get some people that were way out here, and then a lot of people there at the average. Okay, so therefore, you do not have the right to do normal model math. You do not have the right to predict. So you can't say, hey, what proportion of people average above 10 years at a job? Well, you would have to compute this. Well, we do not know what this function is. We don't have the ability to do normal model math on that, so we can't compute it. But look at what the next thing says. Explain why you could do an estimate for the probability that 100 randomly selected people will average out to last 10 years or more. Averaging of 100 people, that's an X bar. Well, that obviously is a very large sample. Remember, to be large enough, it just has to be greater than or equal to 30. So I could have just said 30 people. But once we get the shape of the normal model, and we have these X bars, now it's going to be centered at 6.2 still. However, the shape is fixed. And now that the shape is fixed, I can now then say, hey, here's that 10-year mark. What's the probability that an average of 100 people will have stayed at their job more than 10 years? So once again, do you see the problem? I cannot say what's the probability a person lasted there longer than 10 years, but I can say what's the probability that an average of 100 people lasted more than 10 years. Okay, so that's the difference that you have to pay attention to as you go through problems, is you're reading them and you're wondering, okay, so is this the population where I am just using my population standard deviation? Or is this talking about samples? And then of course, were these samples from a normal distribution or not? Okay, we were safe on that problem with the potato chips because we were told the population was normal. All right. So there's what you have to go by. You are going to be doing an assignment that then practices this notation and then takes you through several problems. Please notice as you go through these problems, part of it is asking you once again to describe this distribution so you can verify the shape, okay, and so on. All right. This is again pretty much weird that this is the end of the learning for this unit. So from now on, it's just practice, and we quiz on Friday, and then we take the test next Wednesday. All right. So good luck to you on this assignment, and I hope that that last part of the unit made sense to you.